Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
How are you, students? Last class we saw that the shapes of atomic orbitals. Let me remind you, the shape of atomic orbitals determined by one of the four quantum numbers, which is known as angular momentum quantum number or azimuthal quantum number, is represented by L value, which is L value 0. It tells us S orbital. L value 1, which is P orbital. L value is 2, D, and L value 3, it means F orbital, and so on. If it is 4, G, and it continues. So what is the shape of S orbitals? Can you remember it? Okay. The shape of S orbital, it has a spherical shape, like this. The higher S orbital differ from the lower one by their large size and nodal value increase. For P, as you know that P has three orientations or three orbitals, that's Px, Py, and Pz. What's the shape of P orbital look like? The shape of P orbital is dumbbell shape. You know dumbbell? It has a shape of like this. This P orbital differ by their three orientations. Peaks along the x-axis, Py along the y-axis, and Pz along the z-axis. What about the orbitals? The shape of d orbital, it has two dumbbells in a clover leaf shape. There are 5 d orbitals. These 5 d orbitals, the 3 of them px, y, pxz, and pyz. Sorry. The shape of d orbital, it looks like a two dumbbell in a clover leaf shape. So the three from the 5 of d orbitals, d, dxy, dxz, and dyz. These three orbitals oriented along the xy plane, not axis. That means between x-axis and y-axis. dxz, it oriented between x and z axis on the plane of xz. dyz, they are oriented on the plane of y and z axis. The two d orbitals, dx squared y squared and dz squared, these two orbitals, they are oriented on the plane of, on the axis of dx squared y squared and on the axis of dz squared. Remember, the d orbitals dxy, dxz and dyz are oriented on z axis. The two dx squared and y squared and dz squared are oriented on z axis. As you see that d orbitals are more complex than p orbitals, f orbitals are more complicated than d orbitals. It was the last class lesson. Let's come to today's class. Today's class is electron configuration and orbital diagrams. What are these electron configurations and this orbital diagram? Electron configuration is the arrangement of electrons on the orbitals around the nucleus within their orbitals, or it tells us the distribution of electrons on the orbitals. But this orbital diagram, they are represented by box, and electrons are represented by arrow, which are arranged within the atom. So the electron configuration for any atom that follows these three principles: the Aufbau principle, the Hand's principle, and Pauli exclusion principle. Let's see this one by one. Aufbau principle, which says that electrons feel from lower energy level to higher energy level. They occupy the lowest energy orbital available before they enter the next one. This one is the principal quantum number, which tells us energy level. Assume nucleus as the center of an atom. This one is the first energy level, principal quantum number n equals to 1, K shell. The second energy level, n equals to 2, L shell. And the third energy level, n equals to 3, L shell, and continues up to infinity. Based on Aufbau principle, n equals to 1, 1s. The first energy level, main energy level, it has one subshell. That's called 1s. As you learned before, this s value can have maximum of 2 electrons. The second energy level, n equals to 2, it has 2s and 2p. S has 1 orbital, p has 3 orbital. Generally, each of them can have maximum of 8 electrons. For n equals 3, the third energy level, it has s, p, and d. S has 1 orbital, maximum of 2 electrons. P has 3 orbital, maximum of 6 electrons, and d have 5 orbitals, maximum of 10 electrons. Generally it has 18 electrons. So one education, we can say that K, L and M shell, and these are the main energy levels that you learned in your lower grade. For n equals to 4, it has S, P, D and F subshells. These orbitals, S have one orbital, maximum of 2 electrons. P has 3 orbital, maximum of 6. D has 5 orbital, maximum of 7. And F orbital have 7 orbitals, maximum of 14 electrons. Generally it has 32 electrons. So electrons fill 1s, 2s, then it comes to 1s2, 2s2, 2p, then 3s, 1s2, 2s2, 2p6. P have maximum of 6 electrons, S can have maximum of 2 electrons, 3s2. Then 3p, 1s2, 2s2, 2p6, 3s2, 3p6. Then it continues to 4s2. 4s. After 4s, it goes to 3d. Then it continues 4p and 5s. 5s, 4d, 5b, 6s, 4f, 5d, 6p, 7f, 5f, 6d, 7p and 8s. It continues. This is how we fill electrons according to the half-power principle from lower energy level to higher energy level. 1s is lower in energy than 2s, 2s is lower energy than 2p, 2p is lower energy than 3s, 4s is lower energy than 3d, 3d is lower energy than 5s, 3d is lower energy than 4p, and 4p is lower energy than 5s. The second principle is the Hund's principle, says that equal energy orbitals. What are these equal energy orbitals? As I said before, P has 3 orbitals, Px, Py and Pz. They are same energy, equal in energy. They are called degenerate orbitals. The same for D. D has 1, 2, 3, 4, 5 orbitals. They are same energy orbital. So according to the Hund's principle states that equal energy orbitals or degenerate orbitals are each occupied by a single electron before the second electron pair up. For example, let's see the electron configuration for carbon, which has atomic number 6. Its electron configuration is 1s2, 2s2, 2p2. S can have maximum of 2 electrons, so 1s2. Says orbital diagram representation. Electrons are represented by arrow, and the box represents that orbital diagram. The upward, it tells us, as you learned from the 4 quantum number, ms, the spin quantum number, which tells us the spinning of electron, whether it's clockwise or anti-clockwise. So it should be put like upward and downward according to the Hund's principle. The second one is fill 2 electrons upward and downward. What about these 2 electrons on P, how they arranged in orbital diagram? Says that electrons must be filled singly before the second electron pair up. Since the p orbitals have degenerate orbitals, semi-energy orbitals, electrons must fill singly. One electron first, then second electron. It should be same spinning. So this one is right, we can say it's correct. What about this one? 1s2, 2s2, 2p. This one is clockwise and this one is anti-clockwise, both of them. That's right. The third one, 1s2, 2s2, 2p2. These two electrons, the first upward clockwise and the second one anti-clockwise. This one is px and this one py. It's wrong. Upward and downward must put on the same orbital. So this is wrong. What about this one? 1s2, 2s2, 2p2, 2 electron. Here the one is upward and the one is downward, but they should be filled singly. This electron comes one here and must be upward. Let me give you another example. Nitrogen with atomic number 7, electron configuration 1s2, 2s2, 2p3. So 1s2, 2 electron at s orbital, 2s2, but at 2p we have remind the Hans rule. Electrons fill single. 1, 2, 3. This is the correct one. But pair up is wrong. But for oxygen, atomic number 8, it becomes 2p4. The fourth electron comes pair up here, and the fifth and the sixth electron for main end fluorine continues, right? Let's see these examples for more information. For hydrogen, it has 1s1 electron configuration, orbital 1s. For helium, 1s2, 2s1, 3 electrons, 1s2, 2s1. For oxygen, has 8 electron, 2, 4, 6, 7, 8. First fill single, then the fourth electron comes pair up, according to the Hans rule. Fluorine, 1s2, s2. Here, one additional electron for fluorine. The second electron comes pair up, and for neon, finally, after filling singly, then it becomes pair up. The same for others. Pauli exclusion principle. According to the Pauli principles, no two electrons can have the same 4 quantum number. No two electrons can have the same 4 quantum numbers. Even if they have 3 of the quantum numbers are the same, the fourth quantum number, spin quantum number, ms, must be different, because when there is 2 electrons in an orbital, the one is upward plus 1/2 clockwise direction, and the second one is downward minus 1/2 anti-clockwise direction. Generally, you can say no 2 electrons can have the same 4 quantum numbers. At least they must be differ from their spin quantum number. Let's see some electron configuration example. Sulfur anion. How could we write electron configuration for cation and anion? As you know, that cation is positive charge and anion is negative charge. Cation positive charge, it means losing of electron. Anion, it means gaining of electron. But for both losing and gaining of electron, only the valence electrons are participate. Only the valence electron lost or only the valence electron added. For normally sulfur is 16 atomic number. For neutral sulfur, if there is no charge, it means no gaining or no losing of electron. Electron configuration becomes 1s2, 2s2, 2p6, 3s2, 4 and 6, 10, 3p, 4. This is the electron configuration for neutral sulfur atom, atomic number 16. This is the electron configuration. But for this -2, it shows that additional electron is added to sulfur atom. It becomes anion. What will we do? The number of p electrons becomes 3p6 because of the addition of these 2 electrons. This is the electron configuration. Copper with atomic number 29. For copper atomic number 29, electron configuration becomes like this. This one is known as the excited or the correct electron configuration or excited electron configuration. Why? Because it's 4s1 and 3d10. It's exceptional. If it is original or the expected, it will be 4s2, 3d9. This is the expected one. But the correct, the excited electron configuration for copper with atomic number 29, 4s1, 3d10. You have to remember the exceptional case. When it becomes copper plus, it is cation. +1 shows that it lost 1 electron. As I told you before, losing of electron, it should be occurred on the valence electron. What are these valence electrons? The valence electrons are the electrons on the valence shell. The valence shell, it means the last shell, the outermost last shell. From copper, which one is the last outermost shell? Principal quantum number 1, n equals to 1, k shell, l shell, m shell, and n shell. So 4s is the outermost shell. So electrons lost from this outermost shell. Then this electron is lost. Electron configuration becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, or we can leave it 3d10. Why these exceptionals are occur? These exceptionals are occur. Some elements like copper, chromium, molybdenum, silver and gold. These elements fill the next orbital to attain stability. Their original electron configuration, electrons excite from ground electron configuration to the next higher energy level to attain stability. All atoms gain, lost, share electron to attain stability, like noble gas electron configuration. The noble gas electron configuration, it is stable. They are neither lost nor gain electron. So the rest atoms to be stable, they do sharing, giving, or exciting. So you have to remember these exceptionals. All the rest elements feel like sulfur, neutral atom. Let's give you activity. Activity to rise electron configuration as use noble gas as a core. For zinc with atomic number 30 and germanium atomic number 32. Try this at your home. Here is the elements electron configuration. We can say almost all elements electron configuration using noble gas as a core. For chromium, which is exceptional, as I said that it fills 4s1 3d 5. Molybdenum, the same, 5s1 4d 5. And the same for silver, gold. You can check it. But why these exceptional elements lost their electron before the next higher energy level to attain stability? How they are attain stability? As you learned before, d orbitals have 1, 2, 3, 4, 5 orbitals. They are same energy orbital, degenerate orbital. if it is 4s2 3d, 4, according to the Hand's principle, electrons fill 1, 2, 3, 4, which is called unfilled. Why it's called unfilled? There is 1 electron is lost here. So to attain, it should be fully 10 electrons, or it should have 5 electrons. That's called half filled. So to attain stability, if it is this 3d4 and 4s2, 1 electron jumps from 4s to 3d and it becomes half filled. So to attain these exceptional elements like copper, chromium, molybdenum, silver and gold, excite their electron before the next higher orbital. So today you learned about electron configuration in the orbital diagrams. Electron configuration, it is arrangement of electrons on the atom, distribution of electrons on the orbitals, and orbital diagram is represented by box, and electrons are represented by arrow, which is represented clockwise upward and anti-clockwise downward. So to write electron configuration, we have to remember the 3 principles: the Aufbau principle, the Hand's principle, and the power exclusion. According to Aufbau principle, electrons are filling from lower energy level to higher energy level. And the Hand's principle, degenerate orbital, same energy orbitals are filling singly before the next electron pair up. According to Pauli, 2 electrons cannot have the 4 same quantum number. At least they must be differ by spin quantum number, which is clockwise and anti-clockwise. It's all about today's lesson. Thank you for your listening and watching. Have a nice day. Bye.